welcome to the lecture series on advanced linear algebra. Today we are going to talk about a special operators, that is called unitary operators. Already we have introduced this terminology in my last lecture while talking about the isomorphism over the inner product spaces. So, let me recall the definition what we have made in my last lectures. Unitary operators. A linear operator T on an inner product space is called as a unitary operator on the space provided it is an isomorphism of the space onto itself. Okay, so what I want to show you, an unitary operator on an inner product space is a linear operator T such that it is an isomorphism of the space onto itself. That is, it is a 1 1 1 2 and it preserves the inner product. So, this implies if U1 and U2 be any two unitary operators, the operators on an inner product space say V over say field capital F, then U1 into U2 is also a unitary operator on V. How? See, since U1 and U2 are isomorphism, so each of them invertible. So, U1 is invertible, U2 is invertible, so the product will be also invertible. This implies U1 into U2, this into means composition basically, is also invertible. Now, we have to also show that the product U1 and U2 preserves inner products. We see we have norm of U1 U2 of alpha can be written equal to U1 of U2 of alpha. So, this is equal to U1 of alpha, which is equal to alpha, because U2 alpha norm of this equal to alpha. We know if U is unitary implies U inverse is also unitary. So, U inverse also exists. So, this implies U inverse exists. So, this implies the set of unitary operators on an inner product space make a group with respect to binary operation as composition. So, say if I consider an inner product space say capital V, if I collect all the unitary operators, then the set of unitary operators form a group with respect to composition as a binary operation. Apart from this, we are also curious to know, is there any relation between unitary operator and its corresponding adjoint operator? I mean to say existence of adjoint operator of a unitary operator. So, to answer these questions, let us give a small results. It is like this in terms of theorem. Let V be an inner product space, I am writing IPS over a field say capital F. Let T be a linear operator on V, then T is a unitary operator, on V if and only if adjoint of T exists and is equal to inverse of T, So, let me give a quick proof of these small results. See, here I am not talking about the V as a finite dimensional or infinite dimensional, I am taking V as an inner product space. So, let us see whether finite dimensional concept is required or not to prove these results. So, let us first consider if part given T is a unitary operator, means T is an isomorphism which preserves the inner product. So, T is an unitary operator. So, this implies for any alpha belongs to V, norm of alpha equal to norm of T alpha, that is T is invertible. So, this implies for any alpha beta belongs to V, inner product of T alpha beta which can be written like inner product of T alpha and T inverse beta, because T into T inverse equal to identity. So, I can write like this thing. This implies inner product of T alpha beta which is equal to inner product of T alpha T inverse beta, which is equal to inner product of alpha and T inverse beta, since T is unitary. T is unitary. So, this implies like this. So, this implies T star, I mean adjoint of T exist and is equal to T inverse, that is T into T star equal to identity, okay, T into T star equal to identity. Now, let me consider the only if part. Given adjoint of T exists, that is T star exists and T star T equal to identity, that is given to us. So, this implies I have to check that T is an automorphism, means T is an isomorphism. So, since T is 1 1 on 2, since inverse exists means it is a 1 1 on 2, and so I can say that it will be in an automorphism provided T preserves inner products. So, for this let me consider for any alpha beta belongs to V, inner product of T alpha T beta, which is equal to alpha T star T beta, which is equal to alpha I beta is equal to alpha beta. So, this implies that T is a unitary operator. T is a unitary operator. So, let me take an examples. Let V equal to the space of all n cross 1 column matrix C n cross 1. I mean to say that is a column matrix over the complex plane, and inner product in V is standard inner product that is inner product of x and y equal to y star x. This is the inner product. Consider a linear operator T on V defined by T of x is equal to A x, where A is n cross n matrix over the complex number C. I have taken this matrix. Now, we want to know under what conditions T will be a unitary operator. Okay. T will be unitary provided for any alpha and beta belongs to V, which is equal to C n cross 1. I will have inner product of alpha beta must be equal to inner product of T alpha T beta, but this is equal to inner product A alpha and A beta. So, this means this is equal to inner product of alpha S star A beta. So, this implies T will be unitary provided A star A equal to identity, A star A equal to identity matrix. See, we have defined the unitary operators. Now, I can also define unitary matrix. Unitary matrix, an n cross n matrix defined over complex number is said to be a unitary matrix provided A star A equal to identity. Here in my definition I have fixed A star A equal to identity. A into A star, will it be identity? I mean, I have seen identity only in one side. If I go A into A star, will it be again I? That are the questions. I will answer these questions soon, but right now I will say that it will be equal to again I. A star A equal to A star, that is equal to identity. I will show you later on, please. So, to answer these questions, so let me give a small results. It is like this. Okay. So, let us talk about one nice results. It is like this, let V be a finite dimensional inner product space, let U be a linear operator on V, then U is unitary if and only if the matrix representation of U with respect to some or every order orthonormal basis for V is a unitary matrix. I did mention one thing, I have told you that isomorphism to inner product spaces we have defined some equivalent statement when the inner product spaces are finite dimensionals. So, here also I will say unitary operator over a finite dimensional inner product space also satisfied all sort of equivalent statement. I mean to say, if U is a unitary operator, then it preserves inner products, implies it satisfies the criteria that it carries every orthonormal basis to orthonormal basis for the space, or some orthonormal basis for V onto a orthonormal basis of the V. So, based on that only I have written here, U will be unitary if and only if the matrix representation of U with respect to some or every order orthonormal basis for V is a unitary matrix. Okay. So, let us give a proof. First is if part, that is given U is unitary. Let B equal to alpha 1, alpha 2, alpha n be an order orthonormal basis for V. So, T alpha 1 to T alpha n will be an order orthonormal basis for also V. Okay. So, we have to show the matrix representation of U with respect to B if it is A. I can write like this, U which is equal to some A matrix A, where A will be an n cross n matrix. If this is equal to A, then A star A equal to identity. We have to prove this one, identity matrix. Okay, consider alpha r and alpha k. So, we have inner product of alpha r and alpha k must be equal to inner product of T alpha r and T alpha k. This is given conditions. Now, from the definition of the matrix representations, we have T alpha r will be what? This will be equal to sigma A I r alpha I equal to 1 to n. T alpha r will be written as a linear combination of the rth column of the matrix A. I mean the coefficient like A1 r, A2 r like that, like this. This is from the definition only. I hope you remember this definitions. And similarly, T alpha k will be what? In the case of k, it will be kth column. So, it will be A j k alpha j, j equal to 1 to n. So, this implies inner product of T alpha r and T alpha k, this will equal to inner product of sigma A I r alpha I equal to 1 to n and sigma A j k alpha j, j equal to 1 to n. Okay. So, this is equal to simplified, we will get over the I equal to 1 to n, j equal to 1 to n, we will have A I r into A j k bar, A j k bar and inner product of alpha I and alpha j. So, we have this ones. According to the definitions, this implies delta r k, which is equal to inner product of alpha r and alpha k, which is equal to inner product of T alpha r and T alpha k. So, this is equal to sigma I equal to 1 to n, j equal to 1 to n, A I r A j k bar and alpha I inner product alpha j, this will be delta I j. So, this means this is equal to I equal to 1 to n A I r and A I k bar. Okay. So, this implies, if I write, this implies if the matrix A equal to write A1, A2, then the column AN, then I have inner product of T alpha r and T alpha k equal to, I have A k star into A r. So, this will be equal to delta k r, This implies that columns of A are orthogonal. So, this implies that A star A equal to identity matrix. Now, conversely, only if given A star A equal to identity, this implies what? Given A star K and A r we call to delta K r, it is given to us. So, this is given like this, then certainly we have inner product of T alpha r and T alpha k will be equal to delta K r, which is equal to inner product of alpha r and alpha k. So, this implies that T preserves inner product. So, T is unitary operator. Okay. Now, based on this, let me define another nice matrix that is called orthogonal matrix. Orthogonal matrix. An n cross n matrix over real or complex is said to be orthogonal matrix provided A transpose A equal to identity matrix. A transpose A equal to this one. Friends, let me also recall one thing here on my while proving the last results, that is if A star A equal to identity, then it will be give me unitary operators. Here A star A equal to identity means we are saying that if I write in a explicit matrix form, then we say that the column, see this is basically this is your A1, A2 and AN, this column will be this row and each column will go to this one row and with the conjugate bar. Okay, so in that case we see that with respect to standard inner product, if I consider over the space, the inner product is x y is equal to y star x, then each column of the matrix A, I mean the set of column matrix of A are orthogonals and the row matrices of A are also orthogonals. So, it will be irrelevant, I mean if I take instead of A star A, even if I take A into A star, then also I will have identity matrix. So, one sided proof implies two sided proof here. I mean I have shown one sided proof of the existence of the inverse, but since the nature of the matrix A such that we can see that even if I go for the other side, I will also have the same result. Therefore, in my definition of the orthogonal matrix, I am saying that if the A transpose A equal to identity, then I will say that it is a orthogonal matrix. By default, it is also satisfying that A into A transpose also equal to identity. So, do not confuse with this one, that is it only one sided, always I have to write A transpose A, or I can also write A into A transpose. This confusion should not be there, and this confusion should not be there because of this principle of this concept of the orthogonal matrix here. So, let us see some example of orthogonal matrix, example of some orthogonal matrix as well as unitary matrices. Let A be an 1 cross 1 matrix, that is A equal to simply C. Then A will be orthogonal provided C equal to 1 or minus 1, because if C equal to 1, then this transpose will be also same, and so 1 into 1 equal to 1, that is 1 cross 1 identity matrix. And similarly, if C equal to minus 1, then minus 1 into minus 1 equal to plus 1. So, that is why if you consider a 1 cross 1 matrix A and it is written like C, then A will be orthogonal provided C equal to 1 or C equal to minus 1. Now, A will be unitary. Suppose you want to check whether it is unitary or not. Unitary provided, what will the condition for unitary? Provided C into C bar equal to 1. So, this implies mod of C equal to 1. So, this implies C equal to e to the power I theta for theta is a real number, real. So, that mod of C equal to 1. Now, let me consider, let A equal to some 2 by 2 matrix, say A equal to A, B, C, D. Now, let us check under what condition the matrix A will be orthogonal. A will be orthogonal provided A transpose equal to A inverse, A transpose equal to A inverse. Let us quickly find out what is A transpose, what is A inverse. This implies A transpose equal to what? A transpose equal to A C B D, and A inverse will be equal to determinant of this matrix equal to A D minus B C, A D minus B C, and this adjoint will be D minus C minus B minus C and A. So, we have the inverse of A equal to like this. So, this implies that A C B D must be equal to 1 upon A D minus B C into D minus B minus C and A. Now, quickly we can check, we can prove easily the determinant of A equal to 1 or minus 1. If you consider orthogonal matrix, the determinant of the A will be equal to either 1 or minus 1. So, A D minus B C will be either 1 or minus 1. So, for determinant equal to plus 1, I will have the condition that A C B D must be equal to D minus B minus C A. So, this implies A equal to D, C equal to minus B. So, this implies your matrix A will be what? A, and suppose B, then C will be minus B and D will be again plus A. So, this is one possible. If the A equal to like this, then I can immediately say that A will be orthogonal, or for determinant of A equal to minus 1 case, A C B D equal to minus D B C and minus A. So, this implies I will have A equal to minus D and C equal to B or B equal to C. This implies my A matrix will be A, B and C will be equal to also B and minus A. So, the matrix will be like this. There are two possible structure for the capital A, for which you will have this 2 cross 2 matrix will be orthogonal. We can also quickly cross check under what conditions it will be a unitary matrix. Using exactly same analysis we can do it. So, we will continue in our next class.